One of the fundamental uses of calculus is finding maximums and minimums of a function. I want to take some time to just kind of go over some of the very basics of maximums and minimums. For instance, what is a maximum and what is a minimum? When we're looking at this graph of f of x, we would say that our maximum is going to occur right here, and our minimum is the lower spot. So maximum, of course, largest, minimum, of course, smallest. Each of these points have an x-coordinate and a y-coordinate. So for our maximum, the x-coordinate is identified at A, and then, of course, its functional value would be the y-coordinate. Similarly, for that minimum, the x-coordinate is B, so the y-coordinate is going to be f of B. So when we're talking about a maximum value, we're going to refer to the value as the y-coordinate, so f of A. And that occurs when x is equal to A. F of x achieves a minimum value of f of B when x equals B. Now, you might be thinking, wait a second, that maximum is not the largest point, because it's just the largest point right over there. If I look to the right of this graph, I've got this point whose y-coordinate is much larger than f of A is, and that's right. What we're referring to here right now is what we call a local maximum or a relative maximum. That locally, in its own little neighborhood here, when we're somewhere right around this point, A, f of A, then A, f of A is the largest or the highest point on that graph. It's not the highest point on the overall graph, but in its local, relative little neighborhood, it is. And the same thing with this minimum. It's not the overall, what we call global minimum, but locally, in its own little neighborhood, it is the lowest point. Now, I said that one of the fundamental uses of calculus is to be able to find those maximums and minimums. So let's take a look at the first derivative in relationship to the graph of f of x. So when we look at the graph of f of x, initially on the left side, we see that everything is rising until we get to that maximum. After that, everything falls, right? Which makes sense, that if you were climbing a mountain, you would climb up the mountain and then you would have to go back down the mountain. So what does that mean for our derivatives? Well, the derivative of f on this first interval, until we get to that maximum, f of x is climbing, so the derivative has to be positive. After that, we said that f of x is falling. That would mean its derivative is negative. Notice that the derivative right at that point, when x is equal to a, that derivative is 0. And that's where we found a maximum. When we get to that minimum, it happens at b. Notice that to get it to be a minimum, we would fall first, and then after the minimum, we would turn around and start rising. So after that point b, we see that the derivative, when it's rising, when f is rising, the derivative is positive. Right at b, this is another case where our derivative is 0. So where do maximums and minimums happen? It looks like a maximum is going to happen when that derivative changes from positive to negative. Notice also that the derivative is 0 at that maximum. When it comes to the local minimum, the derivative changes from negative to positive. And at b, at that minimum, the derivative is 0. So maximums and minimums are going to happen when the derivative is changing, because that means that the original function is changing from increasing to decreasing or decreasing to increasing, which causes that maximum or minimum. So let's take a look at this sign chart. We should be able to identify if this point is going to yield a local maximum or a local minimum. And when we're looking at the derivative, we see that the derivative changes from negative to positive, which means our original function was decreasing, then it stopped, turned around, and went to increasing. And if we kind of visualize this, that sure looks like this point would be a minimum, and it will be. So we say that g of x achieves a local minimum at x equals 2. Now, one of the important things that you're going to have to be able to do is explain why it's a minimum, all right? Be able to justify that reasoning. And we can do it in one of two ways. Now, when we're looking at this sign chart, this is a sign chart for the derivative. So we could justify this minimum in terms of the derivative. That being because the derivative, g prime of x, changes. And we can't say just that it changes. Right? We have to say that it changes from negative to positive. Right? Because the original function has to be changing from decreasing to increasing. And that's the other way that we could justify that this is a local minimum, is in terms of the original function, g of x. We could talk about that change in g of x. That g of x changes not from positive to negative. Because my original function looks kind of like what I have in blue up there. It's going down and then turning around and going up. So we would have to say that that original function g of x changes from decreasing to increasing. So be careful as you're justifying these things to stay away from the word it. You don't want to say it changes from positive to negative or negative to positive, or it changes from increasing to decreasing, or vice versa. Be very specific in what you're referring to, whether it's the original function or the derivative. The derivative is changing positive and negatively. The original function is changing increasingly and decreasingly.